Hello everybody, welcome to our activities for week 5 of MA3343 groups. So we've basically got two concepts again to talk about this week, and they're to do with the concept of commutativity. So basically we know at this stage that groups can be either abelian or non-abelian. If a group is abelian, it means that its operation is commutative, so that for all pairs of elements A and B in the group, composing A with B gives the same outcome as composing B with A. Okay, so examples of abelian groups include things like the integers under addition, non-zero real numbers under multiplication. Groups can also be non-abelian, which means that when you compose two elements, it does matter, potentially, in which order you compose them. So for example, if we take something like a group of matrices under matrix multiplication, like something like the general linear group of 2 by 2 invertible real matrices, something like that, then we know that in general, if we pick two elements of the group A and B, the matrix product AB won't be the same as the matrix product BA. It might be true for some examples, but it won't be true in general. So groups obviously are categorized either as abelian or non-abelian. But if a group has just one pair of elements that don't commute with each other, that's enough to make it non-abelian. And you can't sort of ask the question, well, if a group is not abelian, how badly does it fail to be abelian? Are there lots of elements in it that commute with each other, or are there few? Okay, and the concept of the center of a group, which is the first thing that we'll talk about in this section, is something that sort of tries to get at that, the idea that a group can sort of fail badly to be abelian, or just fail a bit to be abelian. And somehow the center of a group is a concept that measures how close the group is to being abelian if it's not abelian. So let's have a look at the definition. It says that if G is a group with operation star, then the center of G, which is denoted by Z of G, is the subset of G that consists of those elements of G that commute with everything in G. So in other words, Z of G is the set of elements X of G with the property that for every element little g, composing X with little g on the left or on the right gives the same outcome. So for an element to be in the center, it has to commute with everything in the group. Okay, X commutes with G if X star G is the same as G star X. If X commutes with every G, we say that X is in the center. Okay, so that's the definition of the center. It's a set of those elements in a group that commute with everything. So somehow, if the group has a very large center, it means lots of things commute with everything. So the group is close to being commutative in some way. If the group actually is abelian or commutative, then the center is the entire group because everything commutes with everything else. Okay. So just a few examples. So if we take something like G6, the dihedral group of order 6, the group of symmetries of the equilateral triangle, here's the equilateral triangle, and here is its group of symmetries. Here's the table for its group of symmetries. And of course, the idea that a pair of elements commute with each other in a group table means that when you compose the two elements in either of the two possible orders, you get the same outcome. So the way that sort of manifests in a group table is, for example, if we take the rotation through 120 degrees and the reflection in the line L here, we can see that rotation through 120 after reflecting in the line L is the reflection in M. But if we compose the same two elements in the opposite order, then we've got TL after the rotation through 120, and that's this TN. So we can observe that the TN here is not the same as the TM there, although both of those represent, according to their positions in the group table, the compositions of the same two elements in opposite orders. On the other hand, if we take the rotation through 120 and the rotation through 240, those two do commute with each other. Composing them in either of the two possible orders gives us the identity element. So we see that the two elements, these two sort of diagonally opposite positions in the table, are the same. Okay, so basically, if two elements commute with each other, then in the group table, corresponding to that situation, we have a pair of elements in diagonally opposite positions that are the same element. If the entire group is abelian, if everything commutes with everything else, and we're able to write down the group table, then what it means is that if we reflect the entire group table in this kind of main diagonal, we get the same table again. So there's sort of symmetry across the main diagonal. The upper left 3 by 3 portion of this table represents the abelian subgroup consisting of the 3 rotations. And that does have the property that the 3 by 3 part of the table here looks like a symmetric matrix. It has the same positions in every entry in diagonally in these kind of positions that are opposite to each other under reflection in the main diagonal. That's just not true anymore when you expand to the entire group of 6 elements and include all the reflections as well. Okay. So that's how commutativity sort of appears in a group table. I claim here that the center of G6 can be read from the group table and that it consists only of the identity element. Well, justification for that assertion is, if you want to know whether a particular element is in the center or not, and if the elements are listed in the same order, labeling the columns and labeling the rows, which we would typically do for a group table, then if an element is in the center, what it will mean is that the order in which all the elements appear in the row that it labels will be the same as the order in which they appear in the column that it labels. So if we look at TL, for example, the reflection in the line L, look at the 6 elements in its row, TL, TN, TM, identity, rotation through 240 and 120. If we look at the 6 elements in the column labeled in TL, we can notice that they're not there in the same order. TL is first, all right, but the second one is different. The third one's also different. The fourth one is where it meets the diagonal, that's the identity. But the 5th element in the row of TL is not the same as the 5th element in its column, and same for the 6th. So the elements don't appear in the same order here in the row labeling TL as they do for the column labeling TL. That tells us that TL is not in the center, because there are at least some things that it doesn't commute with. If we look through the entire table, we can see that for the identity, as we'd expect, we get in the row labeled by the identity, rotation through 120, 240, LMN. In the column, we get the same 6 elements in the same order. That tells us that the identity element belongs to the center, but you can check for all the others that nothing else does. So the center of D6, they say, is trivial. It consists only of the identity element. Generally speaking, in a group, the center will always have the identity element in it, but it can have more elements than that. Okay, a few more remarks about the center. The center of a group G is the entire group G if and only if G is abelian. Okay, to say that the center of a group G is the entire group G means that every element in G commutes with everything else, which is exactly what it means to say that the group is abelian. Second one, we mentioned this already, the center is typically denoted by ZG. That notation is so standard in group theory that it doesn't really need to be explained if you're using it. ZG is always used to write the center of G. Third comment, this is an important one. It's a technicality, but it's an important one. The identity element always belongs to the center. Okay, why? Well, that's written into the group axioms. Okay, so the specification of what the identity element does in the group axioms is that it's an element which has a neutral property with respect to the operation, both on the left and on the right. So the identity element of G has the property that composing it with any element X in the form identity composed with X or X composed with the identity always gives X. So it commutes with every other element. Okay. So that tells us, of course, that the center of a group can never be empty. It always at least has the identity element in it. Okay, first remark, just by way of example, if we look at the dihedral groups of symmetries of regular polygons, which are one of our kind of nicest families of examples so far, at the center of the group D2n, which is the group of symmetries of the regular n-gon, that consists only of the identity if n is odd. So for example, in the case of the triangle, 3 is odd, D6 is in this category. The center of D6 consists only of the identity, same with D10, the group of symmetries of the pentagon. If n is even, so we're talking about a polygon with an even number of sides, then 2n obviously will be a multiple of 4, and in that case, the rotation through 180 degrees would be a symmetry, and it will also belong to the center, along with the identity element. So I don't expect you to take this statement, just accept it because I've said it. Have a look at the example of the square, D8, and have a look at the group table for the square, and you'll see that as well as the identity element, in that case, the rotation through 180 degrees is another element in the center. D2n, if n is even, so D8 for the square, D12 for the hexagon, will consist of just 2 elements, the identity element and the rotation through 180 degrees. Okay, another example, the center of the general linear group, GL2R, which is the group of all 2x2 invertible matrices with real entries under matrix multiplication. Again, I'm not claiming that this is obvious, but it's worth thinking about. The center of that group is a set of all invertible scalar matrices. The scalar matrices are exactly the scalar multiples of the identity matrix. They're the diagonal matrices that have the same entry appearing in each diagonal position and zeros in the off-diagonal positions. That's just another example, but again, this is not really obvious. It's something that maybe would bear a little bit of thinking about, but you can have a look and see if you agree with that statement, that it's easy enough to see that the scalar matrices do commute with everything because they're just scalar multiples of the identity matrix, which commutes with everything. Slightly harder to see is the fact that the only matrices that commute with all other matrices are the scalar matrices. So somehow the general linear groups are quite far away from being abelian. They have the center consists only of the scalar multiples of the identity matrix. Okay, main property about the center, and this is something that is worth giving some time and thought to, is that the center of a group, as this statement is at least as consistent with the examples that we've seen so far, is not only a subset, but it's actually a subgroup of the group. So this is certainly an interesting fact in group theory. It's also quite a nice one to prove, because I think it's the first time that we've been proving that something is a subgroup purely on the basis of some structural or arithmetic property of its elements. So this is the proof has the usual format for the proof of a statement that says something is a subgroup of something else. The same steps have to be checked, the same things have to be carried out. But I think it might be our first example of a case where we're proving that something is a subgroup purely on the basis of some property that its elements have. Okay, so to show that something is a subgroup of something else, what you have to do is show that that thing is closed under the group operation. You have to show that it contains the identity element, and you have to show that it contains the inverse of each of its own elements. That's what we have to do here. And what we can use in order to do it is the fact that the elements that we're talking about belong to the center, so they commute with everything. Okay, so there's three things to do. First of all, let's start with the easy one. We have to show that the identity element is in the center. That's true by definition, because it follows from the group axioms. The group axioms specify that the identity element must commute with every other element. Okay, second thing, we must show that the center is closed under the operation of the group. And let's give the name star to the operation of the group, just to give ourselves a way of referring to it. So what do we have to do to show that the center is closed under star? We have to show that if we take two elements that are in the center and take their composition under the star operation, that the result of that is in the center as well. What we can use in order to construct the argument is that the two elements separately are in the center. So with these proofs, a lot of the time, really the key thing is to give yourself the right ingredients to show what you need to show. What we have to do to show that the center is closed under the operation of the group is give ourselves two elements of the center. Show that their combination under star is also in the center. So let's give ourselves two elements, x and y, at the center of G. What do we have to do to show that x star y is in the center? We have to show that it commutes with everything. So let's give ourselves an arbitrary element of the group G and figure out what is it that we have to show. We have to show that for every element, little g of G, that x star y starred with G is equal to G starred with x star y. What can we use? We can use the fact that x is in the center of G and that y is in the center of G, and our other knowledge about the properties that are satisfied by groups. This is what we have to show. X star y composed with G is the same as G starred with x star y. So let's write down the left-hand side of that, x star y star G. What can we do with that? We ultimately want to show that it's equal to G star x star y. Well, we've got to start somewhere. So let's start by using the fact that we know our operation is associative because we're in a group. So we can rewrite x star y star G as x star y star G. We really want to move the G from the right to the left of this expression. Okay. Here we've got x star y star G. Well, y is in the center. It commutes with everything. So we know that y star G is equal to G star y. That means we can write x star y star G as x star G star y. Okay, great. We've managed to move the G partly from the right to the left. What else can we say? Well, our group operation is still associative. So x star G star y is x star G star y. There we're using the associativity, nothing to do with the center. Okay. But once we have x star G highlighted like this, we know that x is in the center. It commutes with G. So x star G is the same as G star x. And finally, another application of the associativity allows us to rewrite this expression as G star x star y. Okay, what have we done? We started with one expression. We've rewritten it 1, 2, 3, 4, 5 times. 3 times we've used the associativity property to rewrite it. And 2 times we've used the fact separately that y belongs to the center to get from this point to that one, and that x belongs to the center to get from this point to this one. But we've succeeded in showing that taking the element x star G and composing it on the right or on the left with the element little g gives the same outcome. And this is true for every element little g of G, which is exactly what it means to say that x star y, the composition of x with y, belongs to the center of G, which I really should have written here in the last line, but to fit everything in one slide, I didn't do it. But you can check the current section of the lecture notes, section 2.2, for the sort of fully detailed version. Okay, so there's a lot happening here. I think this, this little section of the proof, it's sort of easy to follow through the steps here and say, yeah, check each one. But to really think about what's going on, I think it's really worthwhile kind of going back to it again and again to say, what are we doing? What can we use? What do we have to show? We have to show that if x and y are two elements of the center of G, then their composition also is in the center of G. What do we have to do to show that? We have to use what it means for an element to be in the center of G. to articulate what we want to prove for x star y, and also to use in respect of both x and y themselves separately in the course of the proof. We can also use any other ones of the group axioms, and the one that we need here is the associativity. Okay, final thing that has to be done. Supposing that we have some element of the center of G, we must show that its inverse also belongs there. So we have to show, we may assume that x star G is equal to G star x for every element little g of G. We must deduce from that that x inverse also has the property that x inverse star G is equal to G star x inverse for every element G of G. So let's give ourselves an element of G. We know that it commutes with x because x is in the center. So x star G is equal to G star x. Somehow from this we must deduce that x inverse star G is equal to G star x inverse as well. What we can do with this equation, this is a statement that's true in our group for every element little g of G. We can take both sides of that equation and hit both sides of it on the left and on the right with the inverse of x. So what's happening from this step to this step maybe takes a little bit of concentration to figure out. What we're doing is taking this equation that we know is satisfied in our group. So these two elements are the same. If they're the same, then they're still the same after we hit both of them on the left and on the right with the inverse of x. So I've skipped a couple of lines here that involve the associativity and so on. But looking at this expression, if you agree that these two expressions are equal, because they were both obtained from two equal expressions by hitting them on the left and right with the inverse of x, then here we can cancel this x inverse with this x, and we're left with G star x inverse. On the right hand side, it's this x inverse that cancels the x, and we're left with x inverse star G. So we can conclude that G star x inverse is equal to x inverse star G, which is saying, and this is true for all elements little g of G, so it's saying that the inverse of x belongs to the center of G if x itself does. So putting together items 1, 2, and 3, here we've shown everything that needs to be done in order to state that the center of a group G is a subgroup of G. This is a really important property of groups. In the case, of course, where a group is finite, putting this together with Lagrange's theorem from last week tells us that the number of elements in the center of a group must be a divisor of the number of elements in the group itself if the group is finite, which is quite a nice fact. The number of elements that commute with everything in a group must be a divisor of the total number of elements in the group in the case of finite groups. Okay, and in general, the fact that the center, the set of elements that commute with everything, form a subgroup is quite a useful and nice feature of the algebra of groups. Okay, that's it for this one. The key things to take away from this one are the concept of the center, the definition of the center, the fact that it's a subgroup of the whole group, and when you have time to think about it, the details of the proof of that fact. Okay. There's no challenge, no video challenge for this particular video. It's a short week since Monday was a public holiday, so we'll just have one challenge this week, and it's coming up in the second video. So thanks very much, everybody, and see you all shortly.